Welcome to section 4 of Principles of Flight. And in this section, we're going to talk about stalling, washout. I'll describe what that is exactly and how that is relevant for stalling. What happens to the stall when we apply ailerons at the stall. And finally, we'll talk about auto-rotation or spinning. So the stalling angle, we already know that if we increase the angle of attack, the coefficient of lift increases as well, and that's a straight line relationship. But that only goes on for so far, and there comes a point where increasing the angle of attack further, the lift isn't increased as well. And that's on the graph. That's the point at which it starts to curve back down again. So beyond a certain point, any increase in the angle of attack no longer increases the coefficient of lift. The stalling angle is the angle of attack of an aerofoil when the lift is therefore at its maximum. You won't get any better lift than at that point. Beyond that angle, the airflow becomes turbulent and the lift begins to decrease. And as you can see in this diagram, the airflow on the top surface of the wing there, in some cases reverses its direction, which is quite normal and obviously a problem for an efficient wing. We talk about the characteristics of a stall and we refer to them in terms of sharp stalls or gentle stalls. So we'll just take a moment to look at what we mean. A gentle stall is illustrated in the top diagram, and you can see that there isn't such a sharp drop away of lift as the angle of attack is increased at the top end of that graph. Whereas in the lower graph, you can see it's a much sharper drop away of lift, and that's really what we mean when we talk about gentle or sharp stalls. Now the nose often drops. In fact, typically the nose goes down at the stall, but it doesn't always, so that's something just to bear in mind. We can have a condition where we have a mush stall where the glider is fully stalled but the nose hasn't gone down. But in general terms, the nose goes down. And that's, as the angle of attack increases, the center of pressure, so the point that the lift is acting, moves steadily forward. And at the stall, this center of pressure moves back again. And it's this pressure distribution change which is causes the nose to go down. So if you remember, in a normal unstalled flight, the weight is acting down, the total reaction from the center of pressure is acting up, and it's forward of the center of gravity. And the tail plane is acting upwards in order to keep the whole thing in equilibrium. However, if we increase the angle of attack to the stall, what's happened is the center of pressure has moved back, as in the lower diagram here, and that turning couple has been removed. So now there's nothing to stop the nose going down, and indeed the tail plane itself is acting in a direction to pitch the nose downwards as well. So you've got a double whammy going on there. Now moving on to washout. Washout is a very simple idea, and it's basically a twist in the wing. So the angle of attack is greater in these circumstances at the root of the wing than it is at the tips. So and you will hear people referring to the angle of incidence. The angle of incidence is the angle between the chord and the longitudinal axis. And it's important that we don't get these two things confused. So the angle of incidence is the angle between the chord line and the longitudinal axis. The angle of attack is the angle between the chord line and the relative airflow. So just keep those two things separate in your mind. The angle of incidence is often referred to as the rigging angle. That's the angle that the wing is set onto the fuselage. At any point in time with washout, the angle of attack is steadily reducing as we move outward towards the wingtip. So, and that's caused by the twist. And what that means is that the inboard section of a wing stalls first, and as we progressively increase the angle of attack, the stall progressively moves outwards towards the tips. So the stall isn't really just a black and white thing. It's progressive, and the more washout in the wing, the more progressive it would be. So, and the huge benefit here is that the turbulent air on the inboard part of the wing is hits the tailplane and the fuselage, and when that gives us those early warnings, so the pre-stall buffet is simply that. Also, if the wing tip is the last part of the wing to stall, the roll that comes from the stall is less, because there's much weaker rolling moment. So it's much better to have a wing that stalls at the root first than at the tip first. If it's going to stall at the tip first, it becomes much more unpredictable and difficult to control for the pilot. But washout also has some downsides, because the lift distribution about the wing is now uneven, because the angle of attack is different along the length of the wing. Then at normal speeds, we get less lift at the wingtips, and that reduces the overall efficiency of the glider, but we have the benefit of a safer wing to fly with. At low speeds, there's more lift at the tip, so as we get near to the stall, the inner part of the wing stops generating so much lift, and the outer part is generating more. And if we go to the other extreme and fly at high speeds, the angle of attack of the wingtip can actually go negative, as shown in this diagram, and then there's a down force on the wing tips and an up force on the parts nearer the fuselage. And you can see that that will clearly have an impact on the structure of the frame, which is why we have things like VNE and so forth to keep us from actually breaking the aircraft in flight. And this will be one of the factors. If we turn the glider upside down, so go into inverted flight, then the whole situation reverses. Washout becomes wash in, and tip stalling becomes much more likely, which is why we'd never recommend that you go off and practice aerobatics without some formal training, because a tip stall is much more likely inverted than the flying the normal way up, and therefore from inverted flight, from time to time you'll hear of pilots who lose control and they effectively flick into a spin, which obviously can be quite dangerous in the wrong circumstances. Let's now move on to the effect of the ailerons and what happens at the stall. And if you consider it, we've got at the stall, if there's a wing going down and obviously the other wing going up, and the pilot were to respond to that, then as the downgoing wing is going down, the response from the pilot, the incorrect response I should say, would be to attempt to raise that wing back up. But what he's actually doing is he's putting the aileron down, which in turn is changing the angle of attack, it's increasing it. So the wing was already stalled, it's now going down in the air more rapidly, which it has actually increased the angle of attack. And then the pilot, just to make matters worse, puts the aileron down to try and raise the wing back up again. So the first action always in a stall situation, wing going down or not going down, is always to move the stick forwards first. Unstall the whole aircraft, and then once you've got normal flying speed, you can roll the wings level. The ailerons also on some gliders have a washout effect of their own, and so the K13s, K6s, K8s, and so forth. That range of models. If you take the stick and centralize the ailerons and then move the stick progressively back until you've got full up elevator, you'll notice that both ailerons go up together. So going from the neutral position progressively back with the stick, you'll see that both ailerons go up together, introducing a swoop onto the ailerons, and this swoop has reduced the angle of attack, and that in turn is delaying the onset of the stall. So it's a very elegant way of dealing with the angle of attack and introducing more washout at the stall, and useful when we're landing, for instance. So as we land, as we're progressively coming back on the stick to hold the glider off the ground during that last part of the hold off, we find that both ailerons start to go up. It introduces more washout at the wing tips, and we're taken further from the stall. It just delays the onset of the stall, and so the landing is going to be at a lower airspeed. Now moving on to auto-rotation, which is basically a spin, and a spin occurs with always from an asymmetric stall. In other words, both wings are not stalled to the same degree at the onset of a spin, and the spin involves movement in all three axes, so in pitch, roll, and yaw. And if we compare the lift and the drag values for the two wings, we'll find that the upgoing wing has got more lift and less drag, and the downgoing wing has got more drag and less lift compared to the other wing. And what the drag does is it increases the yaw. Yaw helps yaw the glider in the direction of the rotation of the spin, and the increase in lift on the upper wing assists with the roll in the direction of rotation. The pitch, the third element, of course, is the move of the center of pressure. As the center of pressure moves back, so the nose pitches down. So we've got this complicated set of actions going on: yaw, roll, and pitch, and this is what is called auto-rotation, and there is a correct recovery procedure, which I won't discuss here. So in summary, we talked about stalling, washout, how the wing is designed to improve or make the stalling characteristics safer for the aircraft, the impact of the use of ailerons at the stall, and we've talked about auto-rotation. More about all of this later. Speak soon. Thanks for watching.